Hello, in this video we're going to be dealing with the shortest remaining time first. Here it is, shortest remaining time first. This one is preemptive. All right. And as we know, the preemption here means that a process can actually stop or execution, or it can get suspended before it's done, okay, according to certain criteria. The preemption can be classified to be time-based and event-based. Okay, shortest remaining time first is event-based. What is the event here? The event is the arrival of a process that has a shorter remaining time compared to the currently running one. Okay, so you tell me it's just arrived. What is the remaining time here? Well, the remaining time in the beginning is the burst. Okay, now if you look at this table, it shows 6 processes. Each and every one of them has its own arrival and its own burst. The first arrival arrives at time 2. This means that the processor is idle from time 0 to time 2. And then process 1 arrives at time 2, correct? Process 1 has a burst of 6. As you can see in the table. At time 4, process 2 arrives, and process 2 has a much less remaining time. At time 4, P1 has a remaining of 4. Why? Because the initial burst is 6, as you can see. You worked for 2 time slots from 2 to 4. So you finished 2 out of 6. So the remaining is 4. And then P2 starts working at time 4 as soon as it arrives. So P2 is going to work from 4, and then it will work all the way to 6. Okay, and it's going to be done. The remaining is 0. You tell me here, but at time 5, P3 arrives. Do you see? And the burst is just 1. Yes, you're right. But P2, at time 5, the remaining time is also 1. It starts at time 4 with a burst of 2. So at time 5, the remaining time is 1. So P2 has a remaining time of 1. P3 has a remaining time of 1. There is no use of context switching. As I mentioned before, context switching is an overhead. Okay, it's a cost that you pay. So why would you pay that cost when you can execute P2? Because P2 and P3 at time 5 have the exact same remaining time. So it would be wrong if you actually do the context switch. Now, when you're done at 6, you have 2 choices, correct? Either P1 that has a remaining time of 4, and you have P3 that has a remaining time of 1. So of course you're going to go for P3 that is going to work from 6 to 7, and it will finish because the whole burst is 1. At time 7, the only available process now is P1. Okay, so P1 will execute from time 7, and it will go all the way until 11, and it finishes. The remaining time is 0. You tell me, but at time 10 we have an arrival here. You're right, at time 10 we have P4, but P4 has a burst of 10, correct? It has a burst of 10, whereas at time 10 the remaining time of P1 is only 1. At time 10, the remaining time is only 1. How did I know? Look, it starts at 7 with a length of 4. So at 8, length of 3. 9, length of 2. 10, length of 1, right? So P1 is the one that is gonna continue, all right? Now let's see what happens at time 11. At time 11, P1, P2, and P3 are done. All right, we have P4 that arrived at time 10, and at time 11, it's the only process there is in the system. So P4 will start executing at time 11, and it's gonna be working all the way until 14, and it will stop. Okay, the burst of P4 is 10, yes, but at time 14, okay, the burst will be 7. Why? It started at 11, so from 11 to 12, that you consumed 1, 12 to 13, you consumed 1, 13 to 14, you consumed 1, so you consumed 3 out of 10, the remaining time is 7. Okay, why did we stop at 14? Because at 14 you have a new arrival, P5, with a length of 6. 6 is less than 7, which is the remaining time of P4. That's why we're gonna go for P5. So P5 is gonna work from 14 all the way to 16 and stop. And the remaining time at 16 is gonna be a 4. Why 4? Because the arrival, it arrived at 14 with a burst of 6. It works from 14 to 15, and then from 15 to 16, so you finish 2 slots. Out of 6, you have 4 remaining. Okay, why did we stop? Because at time 16, we have a shorter process, which is P6. Now P6 is gonna start working from 16 all the way to 18, and now it finishes. All right, now when P6 is done, you have 2 remaining processes. This is P4 and P5. P4 has a remaining time of 7, and P5 has a remaining time of 4. So of course we're going to proceed with P5. So now we're going to go for P5. You're going to start at 18. The remaining time is 4, so you're going to be finishing at 22, and the remaining time is a 0. And then the only remaining one now is P4 that has a 7. You're going to start in 22. With 7, you're going to finish at 29, and the remaining time is 0. Let's do a quick sanity check. What is the sigma here? The sigma of the burst. Let's get it. It's going to be 6 plus 2 plus 1 plus 10 plus 6 plus 2. That would be summed up to be 19, and then with an 8, that would be 27, correct? And then you started at time 2, because from 0 to 2 it was idle, so you finish at time 29, here it is, which is correct. Now let's get the waiting time of each and every one of them, because this is preemptive. The only equation you should be using is the waiting time equals finish time minus arrival time minus burst. So waiting 1, which is the waiting for process 1, equals, when did process 1 finish? Let's look at the table. Here it is, P1 became 0, the remaining time of P1 is 0 at time 11. Do you see it? So the finish time is 11 minus, when did P1 arrive? It arrived at time 2, here it is, minus the burst is 6, here it is. So the waiting time here is 3. How about waiting 2 for process 2. Let's look at the table again. When did P2 finish? Actually, P2 finished at time 6 minus the arrival time is 4, as you can see, right? And the burst is 2, which means the waiting time of this one is 0. Okay, let's see waiting time 3. Look at the table. When did P3 finish? Here it is. It became 0 at time 7, so the finish time is 7 minus, what is the arrival time of P3? 5. What is the burst of P3? 1. So the waiting time here is 1. How about W4, which is the waiting time for P4? Look at P4. P4 finished at time 29. Here it is. When did it arrive? P4 arrived at 10. And the burst is 10. So the waiting time here is 9. How about waiting 5 for process 5? Let's look at the table. P5 finished at time 22. That's when it became 0, as you can see. So it finished at time 22. P5 arrived at time 14. And the burst is 6. So that waited for 2. W6, the waiting time 6 for process 6. Process 6 finished at time 18. P6 arrived at time 16. The burst is 2, so the waiting time is 0. Now, the average waiting time equals 3 plus 0 plus 1 plus 9 plus 2 plus 0 divided by 6, because they are 6. So this is going to give you 3 plus 1, that's 4, and then plus 11, that would be 15 divided by 6, which is going to be 2.5. Okay, this is the average waiting time. How about the response time? Let's do it. Now the response time is not the same as, it doesn't have to be the same as the waiting time. Why? Because it is preemptive. Okay, let's say response time, it's calculated as start time minus arrival time. Okay, so response 1, which is the response of process 1, look at process 1, started, that's the from now, at time 2, and it arrived at time 2. So 2 minus 2, this is going to be a 0. How about response 2 for process 2? Let's look at the table. The very first occurrence of P2 is here. It started at time 4, and it arrived at time 4. So it's going to be 4 minus 4 is going to be a 0. How about response time 3, which is for P3? It started at time 6 and it arrived at time 5. So it's 6 minus 5. This is going to be a 1. How about response 4? Response 4 for process 4, the very first occurrence of process 4 is here in the table. It started at time 11, right? And it arrived at time 10. So 11 minus 10 is going to be 2. Response 5 equals, let's look at 5 here. You will find that 5 here occurs here at time 14. That's the very first occurrence. That's when it started. and the arrival is also 14, so it's going to be 14 minus 14 equals a 0, and then the response 6 equals, look at the table, the very first occurrence of P6 is here. It started at time 16, and the arrival is also 16, so it's going to be 16 minus 16 is going to be a 0. So the average response time is going to be 0 plus 0 plus 1 plus 2 plus 0 plus 0 divided by 6, which is going to be 0.5. That's 3 divided by 6. Okay, how about the turnaround time? If you remember, it's going to equal finish minus arrival. Okay, I'll call it T1, turnaround 1, equal for process 1. When did process 1 finish again? If you look at here, let me just clean those arcs so we're not confused. Okay, look at process 1 and try to find the finish time of it. All right, here. So P1 finished at time 11, as you can see, here it is, right? And it arrived at time 2. So 11 minus 2, that would be a 9. By the way, if you sum the weighting plus the burst, it should give you the turnaround. That's another way to check if your solution is correct. So the weighting 1 is 3. The burst of P1 is 6. 3 plus 6 is 9. Here it is. The turnaround is 9. Okay, how about turnaround 2? Let's see. Turnaround 2 for process 2. Process 2 finished at time 6. And it arrived at time 4. So 6 minus 4, that's a 2. That's why the waiting time of process 2 is 0, as you can see, because the turnaround is the burst, right? How about T3? Look at T3. Let me... So T3, that would be here. Look at process 3. When did process 3 finish? It finished at time 7, right? And it arrived at time 5, right? So 7 minus 5, that would be a 2. It makes sense because the weighting of P3 is 1 and the burst is 1. 1 plus 1 is 2. How about T4? So if you look at P4, when did P4 finish? It finished at time 29. Here, 29, and it arrived at time, let's look at the arrival time of P4, 10. It arrived at time 10. Okay. So the turnaround here is 19. For P5, if you look at P5, P5 finished at time 22 and it arrived at time 14. So 22 minus 14, that would be an 8. And for process 6, process 6 finished at time 18, as you can see, and it arrived at time 16. So here 18 minus 16, that would be a 2. Okay? So this means the average turnaround time is here. You have 9 plus 2 plus 2 plus 19 plus 8 plus 2 divided by 6. So here is going to be a 10, 29, and with 11, that would be 40, 42 divided by 6, that would be a 7. You can also now calculate the CPU utilization. What is the CPU utilization again? It's the sigma burst divided by total time. The burst is sigma burst, let's calculate it. We already did here, 27, and the total time is 29, right? So it's going to be 27 divided by 29. And for the throughput, that is number of processes finished divided by total time. This is going to be 6 because there are 6 processes divided by the total time, which is 29. Okay, this is problem number 1. We're solving shortest remaining time first. Let's solve now problem number 2. It's also going to be solved shortest remaining time first. Here we have P1 arrives at time 3, which means that we have an idle time from 0 to 3, and then we have process 1, all right, that starts from time 3. It's gonna work until time 4. The burst of P1 is 5, so the remaining time is 4. Why? You already did just 1 time slot from 3 to 4, and it has 5 time slots, so the remaining is 4. Why did we stop here? Because P2 arrives at time 4 with a burst of 1. Okay, much shorter than 4. So here P2 is going to work from 4 to 5, and the remaining time is going to be a 0 as P2 will finish. Now, the time here is 5. At time 5, the only existing process is P1, so you're going to be working again with P1. Now you will work from 5 to 6, and the remaining time is going to be 3. Why is this? Because at time 6, as you can see, we have a P3 arrival, and the burst is 2, less than 3. So you're going to continue here, P3, all right, from 6 to 8, right, and no remaining time, so P3 finished. At time 8, you have P4, and what's remaining from P1? P4 has a burst of 5, whereas P1 has a remaining time of 3. So now P1 has a chance to finish. It's going to work from 8 all the way to 11, and P1 is finally done. Now at time 11, all of them are there. A reminder, P1 is done, P2 is done, and P3 is done. Okay, what's remaining is P4, P5, and P6. As you can see, P6 has a shorter time, correct? So now we're going to proceed with P6 from 11 to 13 and no remaining time. And then you're going to take, you have either P4 or P5. They're both as good because none of them executed before, and both of them have burst of 5. I work first come first serve, but if you do it otherwise, that doesn't mean that it's wrong. I'm going to be taking P4. So P4 here is going to execute from 13 all the way to 18, and now the remaining time is 0. And then P5 is gonna work from 18 all the way to 23, and the remaining time is also 0. All of them are done. Now let's get the sigma of the burst. That's gonna be 5 plus 1 plus 2 plus 5 plus 5 plus 2, which is gonna be here 6, 8, 18, 20, right? We started at time 3, we finished at time 23, so that's a good sign, right? Now let's get the waiting time 1 until 6. Okay, again, waiting time is finish minus arrival minus burst. Don't apply any other equation because this is preemptive. So W1 for process 1. Process 1 finished at time 11. Here it is. Sorry. And it arrived at time, P1 arrived at time 3. And it has a burst of 5. Okay. So the waiting time here is 3. Okay. Waiting 2. For process 2, if you look at process 2 finished at time 5. It arrived at time 4. The burst is 1. So the waiting time here is 0. So waiting 3 for process 3. Process 3, as you can see, finished at time 8, correct, here. It arrived at time 6. The burst is 2. So the arrival is, the waiting time is 0. P4, if you look at P4 finished at time 18, here it is. Okay, 18. P4 arrived at time 8. The burst is 5, so the waiting time here is 5. Process 5 finished at time 23. It arrived at time 9, and the burst is 5, so this waited for a 9. Okay, and W6 for process 6. Process 6 finished at time 13. Okay, 13. And it arrived at time 10. The burst is 2, so it waited for a 1. So the average waiting time here is going to be 3 plus 0 plus 0 plus 5 plus 9 plus 1 divided by 6. That's a 3, right? Let me calculate again. Yes, because it's 18 divided by 6. How about the response time? Let's do it. As you know, the response time equals the start minus arrival. So let's calculate now response 1, response 2, response 3, response 4, response 5, and response 6. Okay, response 1 for process 1. Process 1, if you look at the table, we finished at time, started at time 3 here. We started at time 3, and P1 arrived at time 3. So this is going to be a 3 minus 3. This is going to be a 0. Response 2 for process 2. Process 2 arrived at time 4. And started at time 4, so this is going to be a 4 minus a 4, a 0. Process 3 started at time 6 and arrived at time 6, so this is going to be also a 0. Then process 4 started, as you can see, at time 13 and it arrived at time 8. So you have here 13 minus 8, that waited for a whole 5. Sorry. Okay. Process 5, as you can see, it started at time 18. It arrived at time 9, so 18 minus 9. The response here is also a 9. Response 6 for process 6. It started at time 11 and it arrived at time 10. So 11 minus 10, that would be a 1. If you compare the response with the waiting, you will find that the process that started multiple times will have a waiting time different from the response. Whereas the process that started one time and finished will have the waiting equal to the response. Now let's get the average here. So the average response time is gonna be 0 plus 0 plus 0 plus 5 plus 9 plus 1 divided by 6. This is gonna be 15 divided by 6, which is gonna be 2.5. Okay, that's the response time. The turnaround time, I'm not going to solve it for this one. It's very easy. All you're going to do is the turnaround equals finish minus arrival. You're going to calculate it for every process and then get the average. How about the CPU utilization? That's, as we have agreed, sigma of the burst divided by the total time, which is going to be here 20, as we have calculated it, divided by, we finished at time 23. So that would be the CPU utilization. About the throughput, it's going to be the number of processes, which is going to be a 6 divided by the total time, which is 23. All right, that's 2 examples of shortest remaining time first. Next video, I'm going to be solving the round robin.